Remember that we defined a coordination complex as the metal center and all of the ligands that are coordinately covalently bonded to the metal center. And the charge on a coordination complex is equal to the sum of two factors. First of all, the charge on the metal cation, which will of course be positive, assuming we're working with a cation, and all of the ligands present, which will typically be either neutral or negatively charged. And do keep in mind that the charge on a coordination complex may not be equal to zero, and in fact it very often doesn't if the ligand charges overwhelm the positive charge of the metal cation, or the metal cation overwhelms the charge of the ligands. In my experience anyway, charged coordination complexes are more the norm than neutral complexes. Let's work through an example to determine the charge on the coordination complex and the oxidation state of molybdenum in the complex shown here. In this case, we should notice right off the bat that the charge on molybdenum is actually somewhat uncertain. Molybdenum is a transition metal that has access to multiple different oxidation states. So we also need to, in this case, consider the counterions. And this is a general point that's worth making. Very often the counterions will be simple ions that you've seen before. Polyatomic anions, alkali metal cations, relatively simple stuff. And you can assign those charges right off the bat to give you a leg up on assigning the charge of the complex and the metal center within. In this case, I would start by immediately identifying the charge on the sodium cations. Each sodium has a charge of +1. It's an alkali metal, and so it has a charge of +1, always. So the total charge of these guys is +4. That tells us straight away that we can identify the charge on the complex as -4, since the overall compound must be neutral. The overall charge on the coordination complex is the sum of the charge on the metal cation, in this case molybdenum, something we don't quite know yet, and the charges of the ligands. Now in this case we have 8 cyanide ligands. Cyanide has a charge of -1, and so the total charge on the ligands bonded to the metal is -8. Given the charge on the coordination complex, which we deduced from the sodium cation charge, and the -8 charge on the ligands, we can conclude that the charge on the molybdenum must be +4. So this is molybdenum in the +4 oxidation state. When you're doing this kind of charge analysis of coordination compounds, it often helps to start with the counterions, which should be relatively familiar cations and anions that you've seen before. Knowing those charges, you can then go to the charge of the coordination complex as a whole, and then unpack it to identify the ligand charges, and then finally the charge on the metal cation, which is often the most ambiguous and uncertain piece of the coordination complex, given the fact that transition metals have access to a wide variety of oxidation states in many cases.